3. We're talking about hypothesis testing here. And this one here, this lesson is about, is Miss Gallus a good free throw shooter, part 2. So we're going to be using the data that we had 2 days ago in part 1, but now we're going to formalize it into an actual hypothesis test. So in lesson 9.1, we used a spinner to simulate to decide if we had convincing evidence that Miss Gallus was exaggerating about her claim and her free throw percentage of 80%. Now remember that we had, the sample was 50 free throws, so that would have been my N, and Miss Gallus only made 32 of them for a 32 out of 50 of a p-hat of 64%. So 50 free throws, remember, was my N, and then 32 out of 50 was my 64% of p-hat. Remember, p was a hat because it's a stat, and what that means is that I have some data that's collected, and I have conclusion from my data. Okay, so for the first, if you recall, we had a hypothesis test, and Ho was what we are claiming to be true. And what's claiming to be true, what she claimed to be true, what's known to be true, is that the proportion of Miss Gallus's free throws was 80%. However, when we looked at her 64%, we said, okay, when she actually tried to prove it, we're thinking, that's kind of a lot less than 80%. It's definitely less than 80%, but is it significantly less than 80%? And so that's what we're going to check now. So the first thing is, before we actually do a hypothesis test, we have to check some conditions. And so number 2 and number 3 talk about our conditions. The first condition we're going to have to check is if it's random. The reason we need to check if it's random is so that we can generalize to the large population. If we don't have a random sample, I can't talk about anything except what her free throws are right then and there. But I want to talk about all of her free throws and her historical population of all of her free throws and what she would be on average in a long term rather than just her shots right now. So I have to have a random set. The large counts condition is the second thing, and that allows me to be able to have, because that allows me to do a normal model with a standard deviation of right here, if it has large counts conditions. So large count conditions, if you remember, we did it in last unit, is that I have successes and failures to talk about. So successes is, well, I take the number of shots and the percentage of makes, and I get how many successes I got, and I got 40 successes. And the failures, we said failures here, and the failures, which is the number that I attempted, and then the percentage of times I missed, and then how many times that is. And both my successes and my failures have to be greater than or equal to 10. And so the way I get my successes and failures again is the number of shots times the proportion that I made, and the number of shots times the proportion that I missed. And that gets me my successes and failures. And both of those numbers have to be bigger than 10. And if they are, that we are allowed to use the normal model with what I have here, with the mean of the normal model equal to p, and the standard deviation of the normal model equal to square root of p times 1 minus p over n. Okay, so the mean of p, this was just back over here, was 0.8. And the standard deviation is, you notice, it's going to be the same thing. It's going to be p right here. And then 0.2 is 1 minus p, just the opposite of that. And then over 50. And remember, where did I get 50 from? 50 was way back here in my 50 free throws. That's my n. And that gets me this 0.057. Okay, so now we're going to label this normal model. And the way that we labeled this normal model was the 0.8 right here was from my mean. And then what we did to be able to get each one is that I added 0.057 to each one. 0.057 plus 0.057 and so forth and so on, and then subtracted it to get all of these numbers. The next step, what I did was I put our value, which our value is 0.064, and I put it on the graph. And I said, okay, it's about here, and it's shaded to this area here. And so what I'm looking for is I'm looking for this particular probability. Basically, if I threw a dart, boom, to get in on this normal model, what's the probability that it would actually hit this area right here that I shaded? Okay, so the way we are going to do that is we're going to go to normal CDF on our calculator. So to go to normal CDF, it's menu 652. So let's go to menu 652 on your calculators. Let me go ahead and bring one up for us. Okay, bring up your calculator. Calculator page, menu, and it's going to be 6. Oops, I apologize, that was not the right one. There we go, menu. 6 is statistics, 5 is distributions, and 2 is normal CDF. Okay, so if you remember, we have lower bound, upper bound, mean, and standard deviation. Now on my graph, what I'm looking for, lower bound means the most left, that this little tiny area that I have in my green box is shaded. And the most left that it's shaded goes off the graph, so it's any number that's way off the graph. So the number that's way off the graph, I'm just gonna call negative infinity, and you can see that your calculator already has that. The upper bound is where it stops, which ours is 0.64. That's where the shading stopped. The mean we found was 0.8, and the standard deviation we found was 0.057. And so we found a probability of about 0.025. So we found that this area right here is about 0.025 or 0.03. Did I get it right? 2 zeros, there we go. 0.0025. So about that. Okay, so the second thing I'm gonna have you do is to put this in standard deviations. You can see that it's already marked. I'm gonna erase this so we can just see it. Let's just erase some of this stuff here. There we go. I just want you to be able to see here. We're still looking for that same area, but I want you to kind of look here and see what my standard deviations are. So you can see here. So let's just go down to a little smaller. There we go. All right, so you can see from here, 80 is at 0 standard deviations because it's right there in the middle. And then as I went up 1 standard deviation, because I added, remember 0.057, which was 1 standard deviation, I'm at 1 standard deviation. And then added, I'm at 2, and so forth and so on. Same thing here, as I subtracted. You can see that my score of 0.064 is somewhere between -2 and -3 standard deviations. So what I'd like to do is actually calculate exactly where it's from. So what we're going to do that is we're going to do this formula. You will always be given this formula on your test, and this here is what you already have these, so we're going to define these. So P hat, that is equal to your 64% that we found. That's that 32 over 50. That's my sample there. The P naught, this also shows you can just put P, it's fine, but this is from the HO. And remember, HO was P equals 0.8. Let's remind you where that was from. That's just this, okay? And then, of course, there's P again, which is 0.8. And there's P again, which is 0.8. And the N, remember, how big is my sample? And that was 50. Now, we already calculated this from the previous problem. And that's where we got this one here, where we got 0.8 times 0.2 over 50, which was 0.057. And that's where this is going to come right here. So you can see that we got 0.64, which was my P hat, 0.8, which was my P, and then I already calculated that from my previous problem, and I got -2.81. So as I just said, that's my z-score, which means that that's going to be 2.81 standard deviations below the mean, and that's exactly what I got on my graph here. So let's go ahead and do normal CDF. Remember, menu 6.5, let's try it again. Menu 6.5.2, and now I'm going to be using it though with my z-score. So when I try to do it, it's going to be the same thing. If the lower bound is going to be way off the curve, way over here at negative infinity, upper bound this time though is going to be using my z-score at -2.81. So let's try it. So go menu 6.5.2, and again I said the lower bound's way off the curve to the left, and then upper bound is -2.81, and the mean is going to be 0 because you see the mean of yours is of the z-scores is always 0. You see it right here. And the standard deviation, you see I'm going up 1 standard deviation at a time, is always 1. So the calculator already has everything else fixed for you. So I hit OK, and if you notice, I get the same thing. You're going to see the decimals are always off a little bit, but it's essentially the same thing. So about 0.0025. Okay, so you can see the probability of getting the interpret the probability, and it's the same thing. Remember the first step, assuming, you're going to assume this is true. Assume HO is true. Okay, you're assuming HO is true. And then you're going to say there is a p-value percentage. Sorry, that really looks bad. there is a p-value percentage, a probability of getting what we got. We got this in our sample or lower by chance. And because we find that it's lower than the 0.05, which I told you we're going to use 0.05 unless noted, we're going to reject Ho, and we have convincing evidence that she's exaggerating. If we check our conditions, remember we have two conditions. Our first condition is that our data came from a random sample, and that allows me to generalize. And then the second is the large counts rules, where I look at my successes, where I have the times that I attempted times the percentage of times I made it, and then the number of times I attempted times the percentage of times that I missed it. And both of those successes and failures have to be bigger than 10, and that allows me to do a normal model. And the normal model, remember, is going to be my statistic minus my null value, or the value in the Ho, divided by the standard deviation of the statistic. And then you can see that my z-score is equal to this formula, which I told you I don't usually use the p naught, but you can. It just means the p that's in your null hypothesis in the Ho. That's why the O is there. But you can use a p as well. This value will be given to you. You can use table A, which is the z-score table, or you can use, as I did, is menu 652 on the normal CDF model. Okay, let's look at here. Is it better to be last? So if you go ahead and read through this here, you can see that this is basically, I have 12 singers, and each one has an equal probability of being chosen by the audience if it's just by random chance, and so they have a 1/12 probability. But someone's noticing that it looks like the singers at the end have a higher probability of being chosen because they're remembered more by the audience. So that's what it's saying. It's saying, okay, because it found that 59 out of 600 actually preferred the last singer they viewed. So since that's bigger than 1/12, when you see that 59 out of 600 is about almost 10%, and 1/12 is only about 8%. And you can see, since it's bigger than that, that's why they're questioning it. And so number one, ask if I have evidence. And yes, I do have some evidence because it's bigger than it. So therefore, that's some evidence right away. Okay, if I check the conditions, the two conditions we're checking, is it random? Yes, it is a random sample. And what about large counts? Yes, we have large counts, and the large counts means how many successes, how many did actually get chosen, and how many didn't get chosen. And so I have 50 that got chosen and 550 that did not get chosen, and both of those are bigger than 10, so we're set. If I ask you for the standardized test statistic, remember that's this formula here that I'm giving to you, and you have your p-hat. The p-hat, remember, is the value that we got from our statistic, and so that's right here, 10%. And then you can see here, and then you right over here. And that the 1/12 is from my Ho. And then you can see this is, of course, the same thing from my Ho, the P. And then N is the number of samples, and that is 600. If you use table A, which is the z-score table, you'll get this value. If you use menu 652, you get something a little bit different, but really similar. And this is where you get about 9%. So then we have our conclusion, which is because p-value is greater than my alpha, we're going to fail to reject Ho because we have a p-value that is bigger than the alpha level. So we don't have convincing evidence that there's actually an advantage to go last. All right, I hope that helped. And if you have any other questions, please let me know.